Ultrasounds are sound waves with frequencies greater than 20,000 Hz and are not audible to the human ear. One primary use of ultrasound is to scan human body parts during medical examinations. Below here is an image produced during an ultrasound scan. Body parts that are primarily scanned using ultrasound are the heart and the kidney. An ultrasound is a longitudinal pressure wave that requires a medium to propagate through and transfers energy from one place to another. In medicine, the media will usually be soft tissue, muscle, bone, water, etc. An ultrasound is a wave. Therefore, it can be represented by its wavefront and a directed line segment to indicate the direction of energy propagation. However, in medical physics, an ultrasound can simply be represented by a line with a direction to indicate the direction of energy propagation. A single line with an arrow is enough to represent a beam of ultrasound and its direction in which it is propagating. When an ultrasound wave is traveling, the power passing unit area normal to the direction of energy propagation is called the intensity of the wave. When a beam of ultrasound is sent perpendicularly onto the boundary between two media, A and B, where in our case here the incident beam is in medium A, part of the intensity will be transmitted into medium B, and the rest will be reflected back into medium A. For example, if we have water and muscle as our media, then 99.9% of the incident intensity will be transmitted into the muscle, while only 0.1% will be reflected off the water-muscle boundary. If instead we have air and soft tissue as our media, then only 1% of the intensity of the incident beam is transmitted into the soft tissue, while 99.0% will be reflected off the air soft tissue boundary. How much intensity is transmitted and how much is reflected depends on the specific acoustic impedances of the two media. Now let's consider this. Let's say we have an incident beam with intensity I incident perpendicularly from medium A onto the boundary between medium A and medium B as shown. Keep in mind that we are going to be working only with beam incident along the normal to a boundary. The intensity of the beam transmitted into medium B is IT. The intensity of the beam reflected off the boundary is IR. Based on the conservation of energy, we can write I equals to IT plus IR. And if we divide by I, we have 1 equals to IT over I plus IR over I. The ratio IR over I, denoted as alpha R, is called the intensity reflection coefficient. This quantity basically tells us the fraction of the incident intensity that is reflected off the boundary. This quantity is related to the specific acoustic impedances ZA and ZB of the two media. The specific acoustic impedance Z of a medium is defined as the product of the mass density ρ of the medium and the speed c of ultrasound in that medium. Mathematically, this is written as Z equals to ρc. For example, if the medium is water, then we have ρ equals to 1000 kg per meter cube and c equals to 1480 meter per second. And therefore have Z equals to 1.4 times 10 to the power of 6 kilograms per meter square per second. The intensity reflection coefficient alpha R, which is equal to IR over I, is equal to ZB minus ZA over ZB plus ZA and everything to the square. If we have muscle and bone as our media, then we have ZA equals to 1.7 times 10 to the power of 6 kilogram per meter square per second, and ZB equals to 7.8 times 10 to the power of 6 kilograms per meter square per second. In this case here, we have alpha R equals to 0.41. This means 41% of the incident intensity will be reflected into the muscle, while 59% will be transmitted into the bone. When ultrasound wave propagates in a medium, part of the ultrasound energy is converted into heat. As a result, the intensity of the ultrasound decreases with distance. For a parallel beam of ultrasound with intensity I traveling in a medium, after traveling a distance x in that medium, the intensity becomes I dash. The intensity I dash is related to the intensity I by the equation I dash equals to I e to the power of minus mu x, where mu is called the linear attenuation coefficient. For example, if the medium is air, then mu is equal to 1.2 per centimeter, and if x is equal to 4.0 centimeter, then we have I dash equals to I e to the power of minus 1.2 times 4.0, giving us 0.0082 I. Something very important to mention here is that if mu is given in unit of per centimeter, then x has to be in unit of centimeter. And if mu is in unit per meter, then x must be in unit meter in order to have the units consistent. So here we have I dash over I equals to 0.0082, which is equal to 0.82%.